Hello everyone, I am Dr. Belmont and I am continuing the series of videos for my General Chemistry 1 course. So let's jump to our drawing app and let me ask you a question. Do you think that heat and temperature are the same thing? Well, we already know that is not the case, right? They are not the same. And sometimes it's difficult to make the definition of each, but the best way to understand this is actually make a comparison between each of them. So heat is actually a manifestation of what? Of energy, right? And temperature, right? Actually, it's the movement of atoms or molecules, right? And in order for you to move atoms or molecules, what you need, it's energy. Very well. So you can see that they are not the same, but the temperature definitely is dependent on the heat, okay? So let's go and summon someone that you already know, right? A very familiar colleague of mine, Dr. Sticks. Hello, Dr. Sticks. Nice to see you again. And Dr. Sticks is a scientist, as you already know, right? And he likes to be on the ground, right? Close to the soil. But she also likes water, right? And also, since it's already been a very sunny day, we know that pretty close to here, right, we have the sun, right? It's been a very sunny day, and the sun is irradiating energy, right, to Dr. Sticks, to the soil, and to the water. So very well, Dr. Sticks was talking to me about this topic, right? And he told me, hey, I need a little bit of help because I don't understand the fact that the soil, right, it's at 40 Celsius, right? And the water here, right, it's at 26 Celsius. So he's a little bit confused about the thing because the irradiation, it's the same, right? The amount of energy, the change of energy that the sun is giving to the water and to the soil, is exactly what? The same. But the problem is that the temperatures, right, of one substance, in this case soil, and the other one water, right, they are very, very, very different. So what do you think this is? Well, it has a very simple explanation. And the fact is that water needs more energy to rise its temperature, right? Well, in the meantime, soil needs less energy to rise its temperature, right? And basically, all these behaviors depend on what? On the substance itself. Water needs more energy, soil needs less energy. So meaning that water has a higher heat capacity than soil, right? Meaning that water, and this is just a way in which we can interpret things, can retain more heat, more energy in the way of heat than the soil. Okay? And this is what we called in chemistry and thermodynamics heat capacity. Okay? And it has a definition. Heat capacity has a definition, a mathematical definition. And first of all, we need to assign a symbol, and the regular one known is C. And the heat capacity is the amount of heat that you require to change the temperature in a substance. Or you can also say the amount of heat that it is contained in a change of temperature in a substance. Okay, so this is energy, and this is just temperature. Okay, change of temperature. So as you can see, they are absolutely different things. Now, let's take, for example, and set the ground for only one substance. And this is going to help us a lot to understand a little bit more things correctly. And imagine that you have a cube of iron, and this is going to be small, and that you're going to have a large or a big cube of iron, right? And we can already see that this one is smaller than the other one that is bigger. Very well. And let's say that, for example, just because my imagination says, I have 808 grams, okay, of this small piece of iron. Very well. And let's say that for the big one, I have 4,040 grams, right, of this substance. So if I want to raise the temperature, right, since I have less mass here than here, I'm going to need here, let me change, less energy to perform a change of temperature, positive or negative, it doesn't matter. And here I'm going to need what? More energy to perform a change of temperature, positive or negative, it doesn't matter really. Okay, so if I go and measure some of this stuff, I can go and say that, for example, for the small, I was able to perform a change of temperature close to 50 Celsius. And the amount of heat, the amount of energy that I used for that, right, was close to 18,140 joules. That's the one, right? And let's say for the big one, right, I applied exactly the same change of temperature, 50 Celsius, but of course, since it's larger, I'm going to require more energy. In this case, I required 90,700 joules. Very well. So you can see, right, that it's making sense. The small needs less energy. The big one needs more energy to perform what? Exactly the same amount in the change of temperature. So let's go and retake the definition of C, right? So I have capital C, the same as Q over the change of temperature, right? Very well. So, but what about if now we involve the iron, right, in the equation? And now I have, since I am specifying, right, the substance, I need to talk about the specific heat capacity. And for that, what I need to add, it's the mass of the substance, right? Because now I know the substance. So let's say, for example, that I'm going to, sorry, let me rewrite this, horrible. There you go. Now I'm going to draw small c, right? And it's going to be for the small piece of iron. Well, since it's already a specific heat capacity, well, I know that it's what? Q over the change of temperature, but also associated for every unit of mass. So if this is true, and I already know the masses, right, I know that this is going to be 18,140 joules over 808 grams, right, times the change of temperature, which in this case, it's 50 Celsius, okay? And now let's go and do the same specific heat, but for the big piece of iron. And this is going to be, well, the same, right? The same amount of heat that I used to rise the temperature, the mass that in this case is bigger, and delta T. So in this case, it's going to be 90,000 and 700 joules over what? Well, 4,040 grams, right? Times the change of temperature, right? 50 Celsius. And if you perform the math for both of them, you're going to see that they're going to give you exactly the same number, which is 449 joules over grams Celsius. So this is, right, the specific heat capacity for a specific substance, because when we know, right, the mass of the substance, then we can set a very specific parameter, and this is going to remain constant, right? So we have something that is going to be very useful to start developing a concept that it's called calorimetry, right? Very good. Now, different substances have different heat capacities. They are going to be very particular for everyone. So, for example, the specific heat for iron, well, we already know it, is going to be 0.449 joules over gram Celsius. And these are going to be the usual units that we're going to use. Now, if you see, in your book, right, we can have the same specific heat capacity for water, and we're going to see that it is 4.184 joules over grams to Celsius. So you can see that water, right, can storage a lot more heat than iron, right, because 1 gram of water can storage this amount of heat just to change 1 Celsius. And the same here, right? We can see that 1 gram of iron can storage this amount of energy here. And just to take another reference, right, we can look for oxygen, because gases can have the same property too. They are pure substances, right? And it's going to be 900.108 joules over grams and Celsius. So you can see that it's like in the middle of both of them. Very well. So let's continue. So the specific heat capacity, right, we already know that it's going to be known as what? As the amount of heat over mass times the change of temperature. And it's going to identify a substance. But look at this. We can also clear Q and make Q a function of something that we know that is going to be constant no matter what circumstances are. So in this case, Q is going to be what? The same as the specific heat capacity times M times the change of temperature. So why is this important? Well, let's go to a practical example and figure it out. So imagine that you have two substances, right? Two solids, for example, solid A and solid B. And you know that this one is hot, and you know that this one is going to be cold. So when time passes and they reach the thermal, right, equilibrium, we know that the temperature of them is going to be the same. So the temperature of A is going to rise or decrease, so in this case decrease, until it gets the same temperature of B, because B is the temperature of B is going to rise. And we know this because heat tends to move from where? From hot to cold. And this direction is very, 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 very important, because hot or cold temperature is directly related to what? To energy. So the heat, right, of A is going to be higher than the heat that B has. But we know, since they are going to reach what? The thermal equilibrium, that at some point these things need to be the same. So QA needs to be higher. It's going to be hotter, so it needs more energy, and QB is going to be cold. So I'm going to assign a negative sign. Why? Because we need to assign the direction of the flow of the heat. So if this is true, and since I need to apply the direction, right, of the heat, what I am going to do is that to QA, I'm going to assign a positive sign in the equation, and to QB, I'm going to assign a negative sign, right? And now we start getting a proper model, right, of how we can predict the thermal equilibrium for this new system of two solids. So if this is true, and if I clear this equation correctly, I will always know that the Q of A, right, plus the Q of B is always going to be what? 0, okay? Now, remember the definition that we described a couple of minutes ago? Well, I know that what? That QA is going to be the same as what? As the specific heat capacity of A times the mass of A times what? The change of temperature of A. Very well. And I have my substance A, and I can also have what? My substance B. So it's going to be the same as what? As the specific heat capacity for B times the mass of B times the change of temperature for B. Very well. And if this is true, well, let's remember that we have already defined that the Q of A is going to be minus the Q of B. And I know that this is QA, and I know that this is QB, so I can go and substitute this one here and this one there. So let's go and do it. Let's not forget that the change of temperature, right, is the same as what? As initial temperature minus final temperature, and that is something very important, right? Don't lose your sight out of this. Very well. So let's perform the substitution, and continuing with the model, I can say that the specific heat of A times what? The mass of A times what? The initial temperature of whom? Of A minus the final temperature of A, right, is going to be the same as what? As minus, because I have this minus here, and it's very important that you never forget that, times what? The specific heat capacity of B times the mass of B, right, times what? The initial temperature of B minus the final temperature of B. So as you can see, this is quite interesting, because now we have an equation to model what? The flux of heat from A to B. Very well. So let's go and throw a new one, right? And let's complicate things a little bit more. So imagine that instead of having like two substances, now you have three. You have A, you have B, and you have C. And you have A, B, C. Very well. And let's change colors. Very well. It's blue. And let's say, for example, that this one, right, A is hot. Okay, B is going to be warm. And C is going to be cold. So we have a problem, right? Because now the heat can move between any of the systems. So how are we going to model this? Well, remember that heat will always move from what? From hot to cold. That means that we can rearrange our system. How? Well, from hot to cold. And it would be something like this. I have three different systems, substances, to create one system. One is A, one is B, and one is C. And why I'm putting this? Well, because this one is the hot, this one is the warm, and this one is the cold. And the heat will move always, in this case, from left to right. Why? Because it's from hot to cold. And from that you need, of course, right, no matter what, to move from warm. And this is thanks to the direction of the flux of heat. Very well. So let's go and perform the modeling of our equation. So I know that I have the heat of A, right, which is the highest one. And on the other side, I'm going to have who? the Q of B, and the Q of C. And I know, sorry, give me a second, the Q of C. And I know that both of these are going to be what? Less hot than A. That means that I'm going to cut my equation here. I am going to add these ones, right? And both of them are going to be multiplied by a negative sign. Why? Because of the direction of heat. Very well. So if this is true, now I know that QA is going to be the same as what? As minus QB minus QC. And if that is true, then I can clear this equation, and I will always know that QA plus QB plus QC will always be 0. That means that the energy of the system will always remain in the system until the and even after, right, they reach the thermal equilibrium. So if we take this equation and we substitute the equivalencies for that, we can now start modeling a different equation for 3 different substances, right? So we will have our model, our mathematical model for A, B, and C, moving the heat in this case from left to right. So we would have what? CA times MA times the change of temperature of A, which is the initial minus the final. And this is going to be the same as what? As minus, because I have this minus, right? CB MB times initial temperature of B minus T final temperature of B minus, right, because I have this minus, what? C of C, M of C, and multiply this by the initial temperature of C minus the final temperature of C also. And this is the equation that we will use now to manipulate the measurements of calorimetry. Very well, I hope that you have enjoyed this video. We're going to stop it here because I think it's already too long. And I'll see you later soon. Goodbye.